Okay, so let's just get started. Last week we just start to talk about partial derivative. So based on the term derivative, it's just about differentiation, right? But since right now we just face the function with multiple variables, so that's why we need to have partial derivative because we need to know your differentiation is with respect to which uh, axis, which direction. So the partial derivative here is just officially defined as this. So if you just hide y0, you can see it's just like going back to the derivative for single variable. And the partial derivative of f of y with respect to x, x0, y0. So you need to notice that if I ask you to calculate partial derivative, you need to notice that which variable you just going to differentiate with respect to, and especially at which point. So based on the formal definition, it should be followed like this one. Okay, then if we just want to use the geographical representation for the partial derivative, it's just kind of, you can just regard z is equal to f of sy like this surface. Did you remember we just know how to uh, draw the corresponding surface based on the given z is equal to f of sy, right? So just image that this is the surface. Okay, then right now the definition for the derivative is respect to x at s0, y0. So if respect to x, that means for the x direction, it will be varied, it will be variable. But for y direction, we just fix at y is equal to y0. So that means you can just regard, it's a kind of, you just using y is equal to y0, this yellow plane, to cut the surface so that you can just have an intersection here. The intersection here is a curve, right? Then if I ask you to calculate its partial derivative, it just it just treat it as that you just try to calculate the slope for this tangent. I mean the red one at this certain point. Okay, so similarly, if you just respect to if you want to calculate the partial derivative with respect to y, then you can just regard, you just use s is equal to s0 to cut the surface, and you can get the curve. Then you try to get the slope for this tangent at s0, y0. Okay, so this is the original definition for partial derivative. So based on this, you can just, so if you can accept the concept for the partial derivative, then if when we just try to operate the calculation of partial derivative, it's just kind of, when you just partial f partial x, that means you are trying to calculate the partial derivative with respect to x. So in this case, you can just treat s is a variable while y is a constant. Okay, so when you just calculate, when you just differentiate, when you just calculate partial f partial x, you just treat s is variable, but y, s is a variable, y is a constant. So that you can just simply get this result. Okay, and then this time I also talk about implicit partial derivative. The implicit here, just like implicit differentiation. In the past, if I give you s plus blah blah x plus blah blah y is equal to some constant, maybe we cannot have a explicit expression for y is equal to blah 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 s. But we know that there is a hidden relationship between s and y. So just like this one, if I give you blah 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 x plus blah 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 y plus blah 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 z is equal to some constant, just like this one, you can see we cannot explicitly define z as a some blah 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 x plus blah blah y, but we can regard this equation just deliver a hidden relationship between s, y, and z, so that even though we cannot explicitly represent it as blah 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 s and blah blah y, but we can just give a hidden function f of sy as z, so that it just deliver the concept of implicit partial differentiation. So if I give you this equation, you cannot explicitly represent it as z is equal to blah blah blah, but you need to regard z has a hidden s or y inside. So when we calculate partial z partial x, so we can just if you want to get the partial z partial x, then you can try to, based on this equation, you can just try to differentiate its both sides. Then, okay, when you say encounter y, we should regard it as a constant. But you encounter z, please do not treat it as a constant like y, because z implicitly contain x. So you cannot directly just treat it as a constant. So I just noted here, actually z is not a constant. Okay? And actually z also include something about y. So if we just calculate partial y here, you also cannot treat z as a constant. Okay? So after you just treat it as a blah 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 x blah 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 y, then when you differentiate it, y here you just treat it as a constant, so we just keep it here. But z has a hidden x inside, so you just keep partial z partial x here. Okay, for the rest part you can do that. And for the right hand side, you can see x is a variable, so when we calculate its partial derivative with respect to x, then we just directly treat it as a variable, then so we can get the answer is 1. But for y is a constant, so when we take its derivative with respect to x, then we can get the result is 0. Okay, finally we can get the answer. Okay, so this is what we just learned about partial derivative last time. So today we can just move forward, and then I will give you an example. A note. Actually, it's a note. If f may have partial derivatives, but f is discontinuous. Okay, so compared to single variable, I mean for single variable, did you remember if f s y is equal to f of x, f of s is differentiable, then we can conclude f of s is continuous. Did you remember this? Right? In the past, when we just learn calculus, the first thing we learn about is limit, then continuous, then differentiable, right? So as I told you, the differentiable is the strongest one. Then if the function is differentiable, we can say f(x) is continuous, right? But for the function with very multiple variable, even though you have partial derivative, that means you have partial f, partial x, or partial f, partial y, right? But f is discontinuous. I will show you one example, and then later on, I will tell you why it cannot imply f of xy is continuous. So let me just give you an example first. If f of y is defined as 0 when s times xy is not equal to 0. But if s times y is equal to 0, I define it as 1. Okay? So s times y is equal to 0. So all points here is just in. So for this one, let's just focus on x-axis or y-axis. Any point is in the x-axis or in the y-axis that will make s times y is equal to 0. Right? It will make sy is 0, right? So only points on x-axis or y-axis that can happen, right? So in this case, but for other case, it will be s times y is not equal to 0. So let me just draw the picture for you. The picture for this will just lie. Okay, this is x, this is y, and this is z, right? So only when point at this is y-axis, right? This is for x-axis. So any point in x-axis or y-axis, its function, its return value will be 1. So the curve will be this is 1. This is also 1, right? So all points here, its function value will be 1. All point here, its function value is also 1. So when you just try to plot the point, you can get these two lines, right? But for the sy is not equal, s times y is not equal to 0. Let's just include these 4 parts. Then for this 4, its function value will be 0, right? For example, if here is 1, 1, its function value 1, 1, because 1, 1 is not equal to 0. So the return value will be 0. So this point, its corresponding point will be here. Okay. So this is a representation for the f of y. Z is equal to f of y. Okay. So in this case, you can notice that if we get partial f partial x when we focus on 0, 0. This is 0, 0, right? So when we just partial f partial x, did you remember in this case, we just use y is equal to 0 to cut, right? we just use y is equal to 0 to cut the service. Therefore, we use y is so that means we are using y is equal to 0 to cut the surface. So you can just image that, or in this case, because we are trying to calculate partial f, partial f, partial x, right? And then at some certain point, 0, 0. So this is y. So we just use y is equal to 0 to cut the surface. So y is equal to 0 is here. So when we cut it, then we can get an intersection is this, right? When we use the plane to cut the surface, you can get the intersection is this horizontal line. Horizontal line. So if this is a horizontal line, can you tell me what is slope? What is slope? It should be 0, right? Because after you cut it, you want to calculate its slope for this tangent. Then the slope will be 0, right? So the answer will be 0. Okay, so following the same idea, if you just calculate partial f, partial y, then we also focus on 0, 0. So that means you just using s is equal to 0 to cut the surface. So this time, you will use s equal to 0. This is y is equal to 0, right? To cut the surface. So again, you can see the intersection for the y plane and the surface. The intersection will be this horizontal line, right? This time the horizontal will be here. But again, if you want to calculate its slope for this tangent line, is also 0. Right? So based on these two facts, you can find that f has two partial derivatives, partial x and partial f, partial y, right? But you can also notice that because you can see limit as y is approaching 0, 0, f of y should be can you tell me when limit sy is approaching 0, 0, f of y, the answer should be 0, right? When your point is approaching 0, 0 any direction, and you approaching 0, 0, it should be any point on the plane, on the xy plane. So the result here, limit will be 0. But when you just use 0, 0 as the input for f of x, the answer will be how much? If I directly use 0, 0 as the input for this function f, the answer will be 1, right? So you can notice that if the function value is 1, but its limit is 0. So we will say at 0, 0, it is not continuous. Right? So based on this, we can know f of sy is not continuous at 0, 0. But we indeed have two partial derivatives. We indeed have two partial derivatives, but actually the fact is at this point it is not continuous. So not like this one, when we say f of s is differentiable for the single variable function, then we will say f of s is continuous. 好，这边很重要的观念哈，我们在单变数的时候，我们说过，可以微分的话呢，一定就是可以连续，对不对？这可微分是一个已经很强的一个条件了，对不对？可微分就一定连续，可是连续不一定可微分，对不对？之前在上课的时候，在上学期有讲过，对不对？那我们现在学到偏微分嘛，我们想说，那偏微分如果存在的话，那它不可以，也可以说它一定是连续嘛？那这个就是一个反例，答案不是的哈。大家注意看，这函数被定义成这样子的时候呢，他说 f of sy 在 s 乘以 y 等于0的时候，你想想 s 乘以 y 会等于0，只有在哪里？只有在 x 轴上面或者是 y 轴上面，才让 x y 会相乘会等于0。他说在 s 乘以 y 等于0的条件之下的点，它的函数值都是1，那当然就是这一条了，对，或者是这一条 x 轴或 y 轴上面的点呢，可以让这函数值为1。所以大家可想而知，如果是00的话，当然也是在这个点上面嘛，对不对？00也符合这个条件，所以答案它函数值是1，对不对？好，那但是呢 ，sy 不等于0，只要不是在 x 轴或在 y 轴，不是在 y 轴或 x 轴上面的这些点，就绿色的这些点啊，它所投射出来的函数值都是0，也就是都是躺平的。所以大家可以想象，这个它是一个函数哦，但是呢，它有个情况是，只有在 x 轴跟 y 轴上面才有大于1的，就是大于0的函数值1，那其余的是躺平的。所以它的曲面基本上是由这2条黄线跟这个4个绿色的平面4个象限所凑出来的曲面。好，那我们就可以来观察如果我今天要算 f 对 x 的偏微分，在00这一点的 f of x 对 x 的偏微分，刚刚讲过，偏微分是什么概念？偏微分就是如果我是对 x 偏微分的时候，我是拿 y 等于 y0来跟这个曲面做交集，所得到的曲线之后呢，在这一个点上面呢去取它的斜率，对不对？所以很明显的，如果是 y 等于 y0是这个面，对不对？这个红色的面，它跟这个曲面相交集呢，就是这条水平线。那如果要再算这一点的斜率的时候呢，它既然是水平嘛，所以它的斜率当然是0嘛，对。所以如果同样的，如果我对 y 偏微分在00，这时候 y 偏微分 y 把视为变数 ，s 变常数嘛，所以我等于用 s 等于0这条白色的面去切它，切出来一样也是得到一个水平线，所以它的斜率也是0。所以它们2个都可以算出它的偏导数，但是呢，有个现象是，虽然它2个都有偏导数存在，可是呢，在 f of s， 我们在算 f of s 在 sy 趋近00的时候呢，它的函数值是0。注意这个0很重要，不要以为是1号，因为它是 limit sy 趋近00，不是00。sy 趋近00不是0，是很靠近它， 所以当它很靠近它，不管是这样子靠近它，或者是这样靠近它，只要它没有碰到零零这一点之前，它都躺在平面上，躺在平面上代表什么？它值都是零，所以它极限值对 limit xy 趋近00来讲，它的极限值是零。可是我们又根据它的定义是，当你把0跟0带进去的时候，要反映出它这个00的函数值的时候，它偏偏又是1。所以这两条的推理代表什么？其实，在00这一点呢，它是不连续的。哦，所以我们就会看到，即便你有两个偏导数在00，可是呢，事实上呢，它不是连续的。那这问题出生在哪里？发生在哪里？怎么会有偏导数了？我们为什么没办法连续 ？So actually, maybe I can just explain the reason to you. Because when you just consider this partial f, partial x, or partial f, partial y, you just consider these two planes. Did you try to consider if the plane is a little bit slanted? 如果这平面有点斜斜的呢？大家可以想象吗？我现在是这样正切，或者是这样正切，有没有想过斜切？任何方向斜切。如果你任何方向斜切，你都可以保证它存在，它就连续，它就是没有，它就是没有。哦，所以等到今天我不知道我们来得及讲得到，后面会讲到一个 directional derivative。directional derivative 就是方向导数。哦，它讲的就会把各个方向的导数都算进来，不管你要指向哪个方向，算进来。那这时候，如果你的方向导数都存在，那恭喜你就可以回到这个。别忘了我们在讲单变数的时候，事实上单变数的时候，它就只有 x 轴而已，所以其实它只有从左边过来跟右边过来而已，左极限右极限的概念，对不对？因为单一个轴嘛，可是到了一面的时候 ，xy 的时候，它就四面八方靠近这个点，它就不单单只考虑一个单一方向而已，它可能有多方向，所以这也就是为什么你在算偏微分的时候，事实上我们算了它的两个特殊的方向，一个是 x 方向，一个是 y 方向，其实我们并没有涵盖到 any direction。Okay, so this is the first part. Then we can just move to this. If we want to calculate the second order partial derivatives. So normally we will use this notation or fsx to denote this one. This is the second order partial derivative with respect to x. Okay? In this case, it's easy, right? Because you can just treat it as I just calculate the partial derivative for f first. Then I just try to take its partial derivative again, also with respect to x. So this is easy. This is easy. I just want to emphasize that for this case, because we have two directions. So if we get this, just notice partial y will be processed first. Then we will do partial derivative with respect to x. Then, okay? So in this case, we will calculate partial f, partial y first. Then calculate partial based on result and calculate its partial derivative with respect to x. And we also can note it down as this way, y, x. So if the notation just use this one, you need to notice the closer variable we do first. So the closer variable is 1. So we will do partial and partial 1 first. Okay, please just remember. Okay. So if f of s1 is equal to s cosine 1 plus y e to the power x. So when you calculate partial, this is easy, right? We can get the answer will cosine y, because we need to treat y as constant. So when we try to get the partial f partial x, then we can get cosine y plus y to the power e times e to the power of x. So if we just continue to get its second order partial derivative, that means we just calculate this one. Then, so this is 1. So this will be constant. Then this will be y e to the power of x. So the answer will be y times e to the power of x. Okay. So if you want to get partial square, partial y, partial x, f of xy. So in this case, we will calculate partial f, partial x first, right? Based on the notation, right? So that means we can get then partial f, partial y for sine y plus y times e to the power x. So the answer will be negative sine y, right? Because our second operation is for partial y, so that will be we should treat y as a variable, then plus e to the power x, right? So just remember the order. If the notation is like this, partial x first, then partial y, then okay. This is second order. Okay, then I will introduce a theorem to you, but we just use it. We call it the mixed derivative theorem. How is that? If f of sy and its partial derivatives f partial f partial y, partial f partial y, then partial f partial x partial y, and partial f partial y partial x are defined through an open interval containing AB. So that means we are trying to focus on AB, this point. Okay? And all are continuous. At this AB. Then we have a very important property. Then if you calculate partial f, partial x, then partial y, AB, it will equal to partial f, partial y, partial x, AB. The same one. So did you notice that the order has been changed, right? This is partial y first, this is partial, then partial x. But this is partial y first, then partial x. So if you can have the property, if you can have this assumption, then you can just change the order. You can change the order of calculation is partial derivative. Why this is very important? Why this is important? Before that, I will tell you that what is the open interval containing FOSY, containing AB. That means if this is AB, open interval means something like that. This is open region, right? And in this area, at this point, you can keep all are continuous at AB, and also all its derivative is defined here. Okay. So open interval is this one. All points here could be the can make these four functions defined, and all of them are continuous at AB. But as we may know, actually it's hard for us to check this property. But why I just told is this property, this idea to you, because this result is very important. I will show you an example that can shorten our calculation. For example, please just find partial w, partial square w, partial x, partial y if w is equal to xy plus e to the power y over y squared plus 1. So you can notice that the calculation is this one, right? So based on this notation, which partial derivative we should take care of first? Partial y first, right? Partial y will first. Then partial x will the later one. But if you can see, if we just calculate the partial derivative with respect to 1, you can see actually we need to face some complicated operation, right? 你可以看到，如果我们要对外线纤维分的话 ，y 是变数，y 是变数，y 是变数，所以我们在算的时候有点复杂，对不对？但是如果有这个支持呢 ，if we can have the support from this theorem, we can just slightly change its order, become partial y, partial x for w, so that we can just calculate partial y, partial x, then xy plus e to the power of y over y squared plus 1. right? So in this case, if we calculate this one, we can directly get, because this is constant. So when we partial calculate its partial derivative with respect to x, then this part will be 0. Then for this part, we can get y, because y is a constant, s is a variable. Then we continue to calculate partial y, and the answer is 1. Right? So we just change the order like this one. We will, with the support from this theorem, then we can find the order. If the order y, then x has been changed to x first, then y. You can see the calculation becomes simpler, right? But if you just go this first, of course you can do it, but you will face a complicated calculation here. Okay, so this is about section 3. Then I will start to introduce the chain rule for you. The chain rule. Of course, the chain rule here is for multiple variable function. The chain rule, we also knew about this in that semester, right? But at that time, we just faced single variable. So for single variable, if w is equal to f of x, then s is defined as g of t, right? So we know after composite, w could be f of gt, then finally it will become blah 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 t, right? So that we can finally, if we want to calculate, if we want to calculate its derivative, we can calculate dw dt, right? So we can also use the chain rule dw dt, but with the temporal variable dx and dx here, right? So this is for single variable. So if you just regard that as differential, I mean dx, dw, dt, you can regard it as a variable, right? So you can cancel it. Let's go back to the original. So that's how we learn last semester. But this semester, or starting from this chapter, we start to face two variable functions. So if the chain rule for functions of two variables, the upper one is for single variable, but the lower one I also introduced for two variables. So that means if w is defined as f of x1 with partial f partial x, partial f partial y, and s is equal to s of t, y is equal to y of t, right? So that means s is equal to s of t means s is equal to blah 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 t. Y is equal to y of t means y is equal to blah 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 t, right? So if you just use these two to replace here, you can notice that actually finally it will be blah 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 t, right? Something like this one, right? Final result will be w is equal to blah 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 t. The final result still w is equal to blah blah t. But the difference here is the function is defined as two variable function. But here it's a single variable function. So in this case, we still can calculate dw dt, right? Because finally the w is defined by t variable. So dw can be defined as partial f partial x dx dt plus partial f partial y dy dt. So you can just make a comparison from here to here. If you just hide y, it will become single variable function. So it will be go back to this one. Right? If you just hide x, then you will also go back to a single variable function. So then we also can get this one. So when we just encounter two variable functions, this result is just like this one. The original written the original written form should be df dx, right? But right now, since f is a two variable function, so when you differentiate it, you need to tell me which variable you are taking. For example, here is partial x, but here is partial y. So that's why we need to use the partial notation here instead of d, because f contains two variables. Okay, and sometimes you can just memorize as this one, and then please refer to the single variable function. Then you can just see actually they have a very similar expression. And sometimes we also use tree diagram. Tree diagram to express this result. So tree diagram. So you can notice that w is equal to f of xy. So that means w is determined by x, and the center of determined by y. So this notation is just want to express that w can determine by x, and at the same time w is also determined by y. Okay, but x or y, both of them are determined by t. Okay, let me show you again. W is equal to f of sy. So w is equal to f of sy. W is determined by x and y. W is determined by x and y. But x is determined by t because x is equal to s of t. Y is equal to y of t, so that means y is determined by t. And so for this h, you can write it as partial w, partial x. Or you can, of course, it's also fine. Okay? Partial w, partial y. So, or partial f, partial y. Then for this part, there will be only x will be uniquely determined by t. So the notation will be dx dt. Here is dy dt. Then using this one, then adding them together. So you can see partial W, partial X, or partial F, partial X here times dxdt times, right? Then plus partial F, partial Y times dt, d1 over times dt. So you can use this one, but if it's hard for you to memorize it, you can try to use the tree diagram. The tip here is just draw this relationship between the W and SY, and then SY to T. And just use a link to make you easily memorize the chain rule for functions with two variables. Okay, so let's just take 10 minutes break, then go back to the classroom. So now we can just extend the idea to three variables. So this is for chain rule. For functions of three variables. So you can simply extend the idea from two variables to three variables. So we can just three variables. So that means W is determined by f of x, y, and z, right? We try to mimic the process here for three variable. Okay, so W is determined by x, also by y, and also by z, right? But s, y, z simultaneously are determined by t. So we can get here partial W, partial x, partial W, partial y, partial W, partial z, right? Because as I explained to you, why we use partial, because W is not just determined by x only, but also y and z as well. So we need to use partial notation here to determine to see what variable you are just trying to differentiate the W. Then for x, y, z determined by t, so we can have dx dt, dy dt, and dz dt here. So again, times together, times together, times together, then adding them together. So finally, you can get the tree diagram. You just based on the tree diagram, you can get dw dt, right? Why dw dt? Because eventually w will be determined only by t variable. So we will say dw dt. Then it will be partial f or partial w is fine, also fine. You can see here is also partial f, partial, or partial f, partial y here, or partial f, partial z. So in this case, it will be times dx dt plus partial f, partial y times dy dt plus partial f, partial z times dz dt. Okay, here I want to just show you another expression that if you just regard them as you can also regard them as partial f partial x, partial f partial y, partial f partial z. Inner product dx dt, dy dt, dz dt. So this is the inner product. Or so-called dot product. Here we will not use it, okay? But in next section we will use this notation. So please keep this in your mind. Later we will use it. So this is, you can just regard it as this one. But here you just need to notice it was expressed like this one. Okay, so I will give you an example. For example, W is equal to SY and S is equal to cosine T, Y is equal to sine T. So what is the relative value at T is equal to 1/2 pi? Okay, so you can see W is equal to X times Y, but X is defined as cosine T and Y is defined as sine T respectively. So if you just want to get its derivative at T is equal to 1/2 pi, the solution one, you can just use W is equal to XY, then equal to cosine T times sine T, right? Directly just replace as y so that you can get, when you just want to get this one, then you can get this is negative sine T times sine T plus cosine T times cosine T. So that will be cosine square T minus sine square T. So then you can just use when T is equal to 1/2 pi, you can get the result, right? It's not easy for you to just simply use 1/2 pi as an input. So you can do it. But right now, the answer will be, okay, final answer we can get, it will be -1, right? The solution 2 is just follow dWdt is equal to partial W partial X times dx dt plus partial W partial Y dy dt. So in this case, you can get, okay, so partial W partial X. So when you just differentiate with respect to X, remember to treat Y as a constant. So partial W partial X, you will get Y. Right? Then dx dt, S is cosine T. So when you differentiate X with respect to T, then the answer will be negative sine T. So similarly, for partial W partial Y, you can get X then times cosine T, right? Then you still can get the same result, then the answer is still -1. Because you can just use y here, you just replace it back to y is sine t here, s is cosine t here. So here you just directly change the expression from xy to blah 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 t. Here you just use the chain rule for two variables or two variable functions. Okay, so this is the answer. Then, okay, if w is equal to f of s, y, z, but this time s is equal to g of r, s, y is equal to h of rs, and z is equal to k of rs. So we still use the tree. So you can just expect that after we just use this to replace x, this to replace y, this to replace z. So you can expect the final result will be blah 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 r plus blah 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 s, right? Because w is determined by s, y, and z, but s at the same time s is determined by y, r, and s. Y also, k is also. So finally, after you just put all of them into x, y, z, and you can get w should be blah 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 r blah 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 x, right? So if we want to calculate, maybe you will want to know. You want to know partial w, partial r, and partial w, partial s. Right? Because finally w will be determined by r and s. So when you just calculate this, the rating, there are two possibilities. One is for with respect to r, and the other one is for with respect to s. So we can also use the tree diagram to do that. W is determined by s, y, and z. S, y, and z. But s, y, and z can determine by r and also by s at the same time. Right? So again, we just write down some notation on the edge. So here we can partial w, partial x, partial w, partial y, partial w, partial z. Here is the same. But for the lower half, s, y, z are determined by r as well as s. Right? So this time we should note down it as partial x, partial r, partial y, partial r, partial z, partial r, partial s, partial x, partial y, partial x, partial z, partial s. Right? Then just follow the rule we learned. Times together, and name together. Times together, and adding them together. So finally, we can get to 1. 1 is partial w, partial r is equal to partial w, partial x times partial x, partial r plus partial w partial y partial y partial r partial z partial r, then adding them together. So for the right hand side, we can get partial w partial x is equal to partial w partial x partial w partial y partial w partial z times partial x partial s partial y partial s partial z partial s, then adding them together. So finally, we can get this one and this one from these two tree diagrams. So that's why I emphasize, if you cannot, to be safe, you can just draw the tree diagram to make sure your expression can be well done. Okay. So this is for three variable function, but for each variable, each independent variable, they are also determined by R and S at the same time. Then you can get these two terms, this one and also this one, right? Okay, then we will talk about the implicit differentiation revisited. Okay, implicit differentiation, we just learned it from next semester. As I remember, it is in chapter 3. So right now, why we just revisit this problem for about implicit differentiation? Because, you know, in the past, when we talk about implicit differentiation, that is because just like, for example, I give you a function, equation is very complicated, right? Something like this one. This one is very complicated. So I cannot explicitly represent y is equal to blah, 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 x, right? So, but we can get f of xy is equal to 0, right? So this one, so f of xy just defines y implicitly as a differentiable function of x, say y is equal to h of x. Right? Did you remember? Here, that represent f of y is equal to 0. But we cannot just convert it into y is equal to h of x. But indeed, there is a relationship between x and y. So f of y define y. This function just define a implicit as a y. We just define y as implicitly as a differentiable function of x. So even though we cannot clearly or explicitly write down blah 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 x, but indeed we know that we can just somehow we can convert it. It's a hidden relationship, as I told you earlier, right? So here we can say w is equal to these two variable functions. But E is 0. W is defined as f of x, but E is 0. Okay? Then this big F can be determined by x and also be determined by y. Then s and y determined by x. Please note this here. I write it down as x. So if we can just regard y is implicitly as h of x, so y will be determined by x, right? So no problem. Y will be determined by x. But of course, s is 100% can be determined by x. So you can see w determined by x and y, but x determined, y determined by x also. So through this, we can use the tree diagram. Then we can get partial w, partial x, partial w, partial y here. Then here, because it's single variable, it's dx over dx, dy over dx. So using the tree diagram, times together, then adding them together. So based on this tree diagram, you can get the expression as dw over dx is equal to partial w partial x times dx dx dy dx, right? Based on this tree diagram, you can get this expression. Then you can also notice for this part, this will be 0. Why 0? Because w is 0. So when you just try to differentiate it, the result is 0, right? But partial w, this part, we can regard it as big f, partial x. Then here is 1 because dw dx, dx over dx, right? So it's 1. Then plus f, partial y, then dy over dx. So finally, our target is this one, right? Our target. So we can continue to get dy over dx is equal to negative partial f, partial s, partial f, partial y. So this is our final result. So how can we just use that? If I give you x y is equal to 0, then we just regard this part as big f of x1. If we want to get its partial derivative, if we want to get its derivative dy over dx, you can just simply treat it as a two-variable function, then try to calculate big F partial x over partial f big F partial y, and remember adding the negative sign here. Okay, I will give you an example. Of course, here this term shouldn't be 0. Okay, so let me give you an example. For example, please just find dy over dx if y squared minus x squared minus sine xy is equal to 0. So see here, we can just have a hidden implicit expression for y is equal to blah 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 x, right? But we just cannot do that. But we can have an implicit expression. So if we just use the rule we learned last semester, we can just do it like this one. Differentiate at both sides dx dx, right? Then we can, so this time y is the implicit expression for blah 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 x. So when we differentiate this, please, here is not about partial derivative. So y here you should treat it as blah 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 y blah 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 x. So when you just differentiate, you should do 2y to the power 2 minus 1 times dy over dx. The second term is 2x, right? Just follow the rule we learned last semester. Minus cosine sy, right? Because we want to differentiate sine xy, so we can get cosine xy. Then times differentiate x first, but keep y. Then second term is keep x, but differentiate the second term. So the second term we have this form. Then the right hand side is 0. So that's the method. We just put the term with dy over dx together and then put it on the left hand side. To the left hand side. And then we can get 2y minus s cosine sy times dy over dx, right? We have 1 here, contribute dy over dx. Then we also have this term, negative cosine sy times x. This term also has dy over dx. And then put all terms without dy over dx to the right hand side. Two x plus y cosine sy. So we can get, finally we can get the dy over dx is equal to 2x plus y cosine sy over 2y minus s cosine sy. This is solution 1. This is done by the method we learned last semester when we just talk about partial derivative, implicit derivative. But right now we just learn partial derivative. So for solution 2, for the solution 2, we will follow this one. If we want to follow this one, we need to make sure what f of x y is, right? So in this case, we should treat f of x y as y squared minus s squared minus sine xy. So we can use this expression. Let me just write it down here. dy over dx is equal to negative big f of x over big of y. So that when we calculate dy over dx, it will be negative f. Big F is this one. So we can differentiate we can get its partial derivative with respect to x. So here is 0. Then this is negative 2x. Then negative y times cosine xy. So this time we are talking about partial derivative. So when we just treat it, if we just try to get this partial derivative with respect to what x, so we need to treat y as a constant. So that's why when I get this partial derivative for this part, we will get y times cosine xy. So then for denominator, we will have 2y minus 0 minus s cosine sy. So finally, the answer is 2x plus y cosine sy, 2y minus s cosine sy. The same, right? The same. But the solution here are different. For the solution 1, come from partial derivative, implicit differentiation. Solution 2 also come from implicit differentiation, but we just use 2 variable functions. Big F is here, and then we can get this one. Okay, this is for section 4. Okay, we still have some time, so because later I will show you what is the directional derivative. And this idea is very important because, as I told you, when we just calculate the partial derivative, it's just follow some fixed direction, right? But any direction, how can, if for any direction, how can we just get that? So this is about the partial derivative, but it's not that easy to understand that. So let me just show you the concept first, and then we will review it on Thursday. So let me just give you a very quick idea about the directional derivative. This section is very important because this term is important, and also another term is also very important. We call it gradient vector. This is gradient vectors. So let me just introduce the directional derivative first for you. What is the directional derivative? So the derivative of f of s1 at p0 in the direction of unit vector u is the number let me just draw it down, and then later I will show you the whole sum concept as df over ds u p0 as limit s is approaching 0 f of s0 plus u1s, comma y0 plus u2s minus f of s0 y0 over s. So if you just see this expression for your first time, maybe you will see it's a little bit complicated. But no worry, I will step by step to teach you what is the directional derivative. Okay? So before that, maybe I just ask you to notice some important factors. The first one is, of course, for the service, right? So for this part, you can just image that if I give you z is equal to f of sy, of course, you can just form the service, right? This is the first important factor if I give you f of sy. The second term is p0. P0 means s0, y0. So you can notice that this is a point in the sy plane, right? So P0, you P0 here, S0, Y0, right? And the second important factor is unit vector U. So you can see the derivative of f of y, then we can define the surface here. Then P0 is here. Then in the direction of unit vector. So in the direction of unit vector, for example, maybe, for example, U here is like this direction. This is U. So U is expressed as U1, U2, right? So just image that P0 is here, then there is any possibility, right? You may be here, you may be in this direction, you may be in this direction. So you just indicate the direction. So if the direction is here, it will form a cutting plane. Right? If U is U1, U2, or sometimes we can express as U1I plus U2J, right? I remember I just told you how to express the vector by using I and J. I is a unit vector in X direction. J is a unit vector for Y direction, right? So you P0 here, U is this direction, and then you can get the cutting. Okay. Then just use the same concept for partial derivative. For partial derivative, so when we cut, then you can see there is an intersection. Maybe just like here, right? Something like this, right? Something like this. Then we can get the point here. Then we are trying to get, if we want to get the derivative, what is the derivative? It's talking about the tangent line and its slope. is a tangent for the slope. So did you just notice that actually this is a general case. This is a general case. U could be this way, this way, this way, this way, right? But if U is equal to 1, 0, or U is equal to 0, 1, you will go back to the partial derivative. Partial f, partial x, partial f, partial y. OK？ 今天呢，先把这个概念讲给你听，好，然后礼拜四呢，我们再针对这个再讲清楚哈。我最后跟大家讲一下方向导数，这个是非常重要哈。这一章节是非常重要，第5节哈，他讲了两个很重要的观念，一个叫做方向导数，一个叫做梯度向量哈。梯度向量我们后面再讲。那方向导数呢，相较于我们在讲单变数的那个偏微分的时候呢，是对 x 偏微，对 y 偏微。记不记得当初我花了一点力气去画这些图，有没有？这个有没有？当初切的时候怎么切？对 x 偏微呢时候是用 y 等于 y0去切它。对 x 偏微的时候，对 y 偏微的时候是用 s 等于 s0去切它。所以它都是正的，很正的，不是平行于 YZ 平面的，就是平行于 SZ 平面去切的，哦，这是很正规的切法。可是方向导数的时候，它就任意方向了，对不对？那任意方向，你总要告诉它是什么方向啊 ？OK， 所以呢，如果要你求这个函数，这个曲线 z 等于 f of sy， 它在 P0， 注意看它只有2个元素，所以代表它就是 xy 平面上的点。这个是 x，y 这是 z。我一定会告诉你一个从 P0 点在哪个点上面。同时呢，我要告诉你一个方向，这方向是单位向量，它可以指出你这个是往哪个方向切。哪个方向长，对不对？也有可能是这样啊。如果我的方向导数给的是这样呢，我的 u 搞不好是给的是这样呢，对不对？这是另外一个 u 啊。那你的切平面就会变成这样子了，对不对？不好画了哈，这不好画，就变成这样切。曲线面跟实线面是它2个切的。曲面是固定的，但是你是这样切，还是这样切的时候，跟它所交出来的曲线就完全不一样。虽然它们都通过同一个点 P0， 对不对？如果你的 U 是这样子切出来是直的，如果 U 是这样子切出来是曲的这条面啊，因为它画在一起不太好。但是你可以想象，他们都可以做出一件事情，就是这个面，这个切面。就是去切人家的那个面哈，跟这白色的曲面呢，他们会有个交线出来，这是交集，就是这个橘色的线。那这件事情呢，所谓的导数呢，就是在讲，当你这样交集出来这条线，我想知道这个点哈，这个点是谁呢？这个点是 S0 Y0 的 f of S0。经过这一点的切线的斜率，所以你可以想象，因为你是这样子切，跟这样子切下去，它的交线一定会不一样。交线不一样，它的切线自然就不一样。它切线不一样，它的斜率自然就不一样。这很重要。那这个观念有之后呢，我们再讲到 gradient vector 的时候，你就可以更清楚了。那我们先给大家一个这个基本概念，因为怕再把这变数导进去，你就看得更模糊哈。好，那我们今天就先上到这里哈。那回去先把这个理解一下哈，跟这个偏微分的地方互相呼应，先学一下。好，那我们今天就上到这里。